Hello, and welcome to Module 11, Network Communication Devices. Excuse me. So today we're going to be concentrating on really routers and switches and some wireless devices and how they operate and what their responsibility is. So this way you'll be able to understand how to protect them. All right, so let's get started. Remember, we're going to be taking notes. Don't forget that. Make sure you have a Word document open for you. Okay, so let's talk about end devices. When we talk about end devices, anything that is attached in a local area network switch, servers, workstations, laptops, desktops, those are workstations, that's where you do your work, IP phones, anything that is, you communicate at the end in a LAN, that's called an end device, okay? So I think that's, sometimes we call these nodes or hosts. Nodes, hosts, end devices all mean the same thing. So write that down. End devices is equal to hosts is equal to nodes, right? Okay, so take a look at the video whenever you get a chance. The next thing is we need to talk about is routers. As we have discussed earlier, something that is analogous to a router is the post office. And the post office responsibility is when it receives a package, it looks at the destination zip code and try to find where to send this package to according to the zip code. So what the post office looks up, types in the zip code, assuming that's the scenario, looks up in the chart to see where is the zip code located. And if it's located west, he'll repackage it and send it to another post office that is west of it, right? And vice versa, it keeps going that way. So the router, what it does is it looks at the destination IP address, but it will mask the host portion of the IP address and only look at the network portion of the IP. And then look up a chart called the routing table. And according to the chart, then the router will re-encapsulate the packet into a WAN frame and send it to another router, right? So let's say here, you send your data to your default gateway. Your default gateway looks at the destination IP address, and then we'll pass it to this router. This router will pass it to multiple routers within the internet, and ultimately we'll get to this router and then into your LAN. That's the main responsibility of the router. So how did the router get these network addresses? How does it know where to send the package to? So this is when you type the command on your router, show IP route, you are displaying the routing table. There's a directly connected network to me. That's the letter C. These are the codes for it. Connected network 192.168.10/24 is directly connected to my fast Ethernet 00. That's what it's saying. So if he gets a packet with the destination IP address, whatever the destination IP address, he grabs the IP address. Now listen to what I'm saying. This is exactly what the router does. He gets the destination IP address that he receives. He goes to the first entry of the routing table, /20, and picks up the mask, puts it under the destination IP address of the packet that he just received, and he does the logical ANDing. And why does he do that between the IP address, the destination IP address, and this first mask? Because he wants to mask the host portion of the IP. When he does the logical AND between the destination IP address that was on the packet and the first mask, what reveals is the network portion. So what's revealed, and he compares it to this address. If it's this address, if it's not this address, then he moves on to the next, and he does the same thing. So, and he moves on to the next. If there's a match, then he will send it. So let's say there was a match in the very beginning. When there is a match, he will send the packet to this interface, the fast Ethernet 00. So what does the fast Ethernet 00 says? he will send an ARP request to everybody in the LAN. He will say, hey, I have a packet for somebody with this IP address. Please give me your MAC. So let's say it was for this guy. This guy responds back with an ARP reply, gives your default gateway your MAC address. He puts the packet that he receives in a frame, stamps the destination MAC address of this guy. He puts his MAC address on it, and he sends it to the switch. What does the switch do? Looks at the destination MAC address that's stamped on the frame, and he knows that this destination MAC address is located at this port. So he sends the frame to him. What does he do with the frame? Verifies that it's his, because he looks at the destination MAC address, opens up the frame, pulls the packet out, verifies that it's his IP address, opens the packet, pulls the segment out, find out what sequence number it is, and what port number, what application. And he waits for all the packets to come in, then he reassembles everything and gives it to the application layer. How is that? All right. So please write the first bullet point. Routers' primary functions are path determination and packet forwarding. So they look at the path determination. So this is where they look up which path they're going to go to. And packet forwarding. They packet the forward depending on where they're going to go, right? That's the primary job, is to look up what destination they need to go to and send it to that interface. Okay, now, of course, routers can do other things like you can set it up as a firewall, you can set it up as a DHCP server, you can set it up, as an IPS system, IDS, a whole bunch of other stuff that you can have it do if you want to. It could be a AAA server as well, but we can discuss that some other time. All right. So we just explained all of that. So write these this bullet point down here, these 3 bullet points. So what does it do when it receives the packet? It decapsulates it, opens it up, and so on. Okay, like we discussed earlier. All right, so this is exactly what I said. This guy wants to encapsulate the data. He encapsulates it, puts it on a PC, sends it to his default gateway. Your router opens up the packet, right? He opens up the packet and determines where to go, which interface. It needs to go to this interface. We encapsulate it into another frame here and sends it to this guy. This guy opens up the packet, looks at the destination IP address, and decides it has to go to this interface. Re-encapsulate it into another frame and pass it on. Okay, so that's exactly what's happening when it goes from one router to another. Here, write this down, even though it's not here. Packets are encapsulated into frames as they change frames. The packets change frames as they traverse the network. So write this down. Packets change frames when they are traversing the network. All right, so packet forwarding decision. If you look at the destination packet, so you look at the destination IP address, like I said, then you decide. Right? Just like I explained it to you. Just go back forward, fast forward to the beginning when I started talking about that routing table. The only thing I did not go over, let me show you. Let me just go over it one more time. Just one thing I forgot to tell you is that here's your routing table, right? If I go through every single one of them and there is no match because the gateway of last resort is not set, then your packet is thrown in the garbage, in the trash. And then the ICMP that's running on the router will send out an ICMP packet back to you, say that the network is unreachable. Remember that we talked about ICMP with a specific code? When you see the network that you're trying to reach is unreachable, meaning that there is no route. These are routes in the routing table. So you have to do a default route maybe in here to allow it to do it. The letter S, by the way, that means somebody typed this route, told the router, listen, if anybody comes into you with a packet and it wants to go to 192.168.3.0, please send them to this interface. That's what this is saying. It's only one hop away from you. Will be this. Okay, so hopefully you've seen this in your CCNA class when we were talking about routing. So that's pretty much it. This is a routing table. You either type it in or directly connect it, or it'll be dynamically learned from other routers. Dynamically learned, those routes, is when routers talk to each other using routing protocol like OSPF, EIGRP, or RIP, or so on. All right, so let's move on. So that's when they are deciding, and then the packet will re-encapsulate the packet. So we forward the packet directly to a connected network, to a next hop router. And if there is no match, you drop the packet. But remember, the ICMP will send out a packet back to you telling you that the network was unreachable. Because that's, remember, ICMP stands for Internet Control Messaging Protocol. He's the manager. He has to let you know what happened to your packet and why it did not reach its destination. Please write the 3 bullet points, this sentence and the 3 bullet points. What does the router do with a packet when it receives it? Okay, so pretty much the same thing happens with IPv4 and IPv6. Remember, when I get a packet, there's an ARP request. You want to get the MAC address. You cannot send a packet to anyone unless it's encapsulated in a frame. And if the packet is in the frame, you need to have the destination, the person that you're sending the data to, the end device, you need to have his destination MAC address stamped on the frame, and your MAC address, of course. So the packets have to be encapsulated on a frame before it's placed on the media. What is the media? The media is either the copper wire, the auxiliary twisted pair wire, coax, fiber, or could be wireless. Packets have to be framed. And on the frame, you put the MAC addresses. Pretty much the same thing happens with IPv6. Instead of using ARP, they'll use what we talked about earlier, the neighbor solicitation and neighbor advertisements. Pretty much the same thing. Okay? So it can forward it to the next hop. If there's a match in the routing table, you send it to the next router, but you have to encapsulate it in a frame, right? Or you drop the packet because there's nothing in there. Nothing in the routing table that tells it. All right, so the directly connected ones are the ones that have little c. So this is very important, so please write these down, these two. The routing table will store information directly connected and remote routes. So the directly connected, this is very important. I want you to write this down. When you configure a LAN interface on a router and you type no shut, you activate it. It immediately, the router will place a route in the routing table with that IP address, with that network address that you did. And it will put a little C next to it, meaning that I have a directly connected network that is active, because that's the default gateway for everyone that is connected to it. Okay, so that's what directly connected routes mean. If you type shutdown on the fast Ethernet 00 interface, then the route in the routing table will be gone because it's closed. Even though the devices are communicating inside, they don't have a default gateway. They can't go out and nobody can talk to them from the outside. All right, so here's your default gateway. Okay, so when I type 192.168.10.1, right? And I say with the mask, 3255s and a 0, and I say no shut, immediately in the routing table, you'll have a little C, and it will say 192.168.10.0/24 is directly connected to fast Ethernet 00. Same thing with this. 192.168.11.0/24 is directly connected to fast Ethernet 01. And this interface will say 209.165.200.225/30 is directly connected to serial 000, for example. Those are 3 directly connected interfaces, and you'll see 3 C's on them. These are remote networks, right? So this guy may say 110.110.110/24 is 1 hop away. And if anybody wants to send data, I should send it out of this interface or send it to this guy, the next hop. This is the hop, okay? So local interfaces are added when an interface is configured and active. This entry is displayed in operating system 15 or newer. So you'll have for an interface or an interface that will say exactly the same interface with /32 IP address, the actual local route interfaces. So in case routers or anybody needs to communicate directly with the interface itself. Static routes are the ones that you type in. We talked about directly routes. Dynamic routing protocols is where you don't get involved. All you tell the router is you enable, let's say, the open short path first on all the routers. And we'll talk, I think we talked about that in the CCNA course. And if you haven't, you will. So routers will talk to each other according to the protocol OSPF, and they will configure their own routing table. And it's dynamic, and they will change, update themselves. You don't have to do anything. So it's really nice. Okay, but they require more memory. This is an open protocol that everybody uses. It works on non-Cisco routers, but this is till 2013 was Cisco proprietary. No one can also use the EIGRP. And then Cisco in 2013 opened it up, so it's now an open source. But it's now it might be a little too late for Cisco because most routers, Cisco and non-Cisco, only use OSPF. This is the most widely used for private WAN connection. Okay, so there are other routing protocols. Please take a picture of this for dynamic routing protocol. The ones that measure distance vectors, the EIGRP or RIP. RIP is the oldest. Version 2 is for IPv4. Next generation, RIP-NG is for next generation. EIGRP, and then you got EIGRP for IPv6. Version 2 of OSPF supports IPv4 VLSM, just like RIP 2. And version 3 is for IPv6. ISIS, nobody really uses this. And for exterior gateways, this is BGPs, the Border Gateway Protocol, are mainly used connecting between, let's say, ISPs for the internet, for big networks. So take a picture of that. I don't want to go into this. This is, takes a whole semester by itself discussing the routing protocols and how they operate and configuring them and troubleshooting them and so on. So at least you should be familiar with those. Okay, so end to end. So you want to send a packet from this end to this end. So let's talk about that. I'm going to go through it, just taking this picture so you'll understand everything. So if you need to review, you go back to where I'm going, what I'm saying right here, even though we might be zooming through a few slides after this. Okay, so the first thing you are going to do is, let's say you want to communicate with this guy. This PC1 wants to send data to PC2, and somehow using the DNS, he has the IP address of 192.168.4.10. How did he get it? Maybe he got it through his DNS server. So he stamped it as the destination IP address. He puts his IP address in here. How did he get his IP address? He got it from a DHCP server. All right, so from here to here in the gray, that's the packet. Okay, so the PC now got the packet, PC1. Now he puts it into a frame. So puts the trailer on the frame, and he puts, this is the data of the packet, and he puts in the type 800. That means this packet that's in here is IPv6. He puts his MAC address on there, but now he needs the MAC address of this guy. So before he puts this in. So he sends out an ARP request to everybody in the LAN. Nobody responds because no one has this IP address 192.168.4.10 in his network. This is 192.168.1 network. So nobody responds. By default, PC1 will request the MAC address of his default gateway. Why? Because nobody answered and gave him a MAC address. Nobody replied to his ARP request. So your default router will respond back with his MAC address, and that's why he got the 0010 as the destination. Remember, that packet is not destined to the router. You just send it to his default gateway so he can route it for him. So now this whole frame with the destination MAC address and the source MAC address of the PC1 is stamped. You send it to the router. The default gateway will get it because his destination MAC address is on it. He opens up the packet and looks at the destination IP address, which is right here, right? And when he looks up the chart and does the masking, he finds that he should be sent out of G001. So he will request the MAC address of this guy to send it. He will encapsulate, put his MAC address 0020 as the source, and put the destination 0B as the destination, and then the frame is sent to here. And same thing will happen. This router will open up the frame, look at the destination MAC address, puts it into a new frame, and then we'll put his MAC address as the source, his MAC address as the destination, and send the frame to him. And when he gets it, he looks at the destination IP address and he says, okay. He sends out an ARP request to somebody in the LAN. This guy sends him his MAC address, 0B20. He puts it at the destination. And R3, he will put his MAC address as the source and he'll send him the frame. You see, that packet never changed. It was just re-encapsulated into new frames as it traverses the network. Okay? So that's what this is all trying to tell you. Okay, you can watch the video and hopefully that will make sense. Hopefully. All right, please review that again. Okay, so let's talk about routers are considered to be layer 3 because they inspect the IP packets, and IP packets are layer 3 PDUs. They inspect the labels that are stamped on the packet. They are able to get inside the frame and pull the packet out. That's why we call them layer 3, because they work with layer 3 packets. On the other hand, a switch only operates with the frame that is sent to it. So it matches the data that's on, it looks at the labels that are stamped on the switch itself. So this is a layer 2 device because it reads the labels of a frame, and a frame is a layer 2 data link layer data, PDU we call it, protocol data unit. The bridge really is nothing but a switch, 2-port switch. So this is just a multi-port bridge. So a bridge is like a switch with 2 ports, nothing else. A hub, so this is also a layer 2 device. A hub is a layer 1 device because what it does, there is no software in a hub. A hub when it receives a packet, he doesn't look up anything. He just sends the data to everybody. So the more people are connected to the hub, the slower your connection is going to be. This is called one collision domain because only one person can talk. There's no software. This is all circuitry. This is a layer 1 device. It's all hardware. It's all wired so that one port is connected to every other port. So when one frame comes in, it's sent to everyone. the bridge on the switch, or the bridge on the other hand, when a frame comes in, the switch has the software to look up the MAC address. The destination MAC address is stamped on the frame, find out which port, and send it immediately only to that port. Okay. All right. So that's the switch operation. All right, so let's get into a little bit of more detail of how the switch operates. So let's say the switch receives a frame from here. The first thing that the switch does on port 1 is it looks at the source MAC address, 000A. So when the switch reads this IP and this MAC address coming from port 1, in his MAC address table, he's going to say 000A is located at port 1. Why? Because I looked at your source MAC address and you're coming from in here. All right, so write the first bullet point. Write all these bullet points. That's very important. The next thing that he does is he looks at the destination MAC address and then looks up his chart. He sees that 00D is not in his chart. What is he going to do? He's going to send the data to all the port. That's called flooding. Then this guy is going to obviously receive it because he is on switch. When he gets it and he responds back, then the switch will learn that 000D is located at port 4, right? So now the MAC address table is filled. Next time you send a frame, he looks up the chart, he sees that 00D is located at port 4, and he will send it only to port 4. See that? By learning the source MAC address of an incoming frame, the switch populates its routing table. So write this down in addition to all of this. By examining the source MAC address of an incoming frame, the switch will populate the MAC address table. That's how the switch learns what MAC address is located at what port. Okay, so let's see what's going on here. All right, so there you go. You're flooding everybody. And then after that, you respond back. Okay, what is a VLAN? A virtual, well, what is a regular LAN, not a VLAN? A physical LAN, let's say. The switch itself is one local area network. So what is a local area network? When you send a frame to the switch, well, let me go back. It's probably easier to explain it here because you can see the ports. So let's say this switch, because I can send the data when I send the broadcast frame, that means a frame that has the destination MAC address with all ones in it, 48 ones. When the switch receives a frame with 48 ones, it sends it to everybody. That means everybody's on the same local area network. That's what a LAN is. If you receive a broadcast message, you and the person who sends you that broadcast message are on the same local area network. So a broadcast domain is the same thing as a LAN, right? Virtual LAN, so let's say I can split the switch into two. So when I send the broadcast message, only these two people get it. And when this guy sends the broadcast message, or this guy, they both get it. So you separate the switch. They're virtual LANs now, because on the same physical switch, but you have two switches really, two virtual switches. So a VLAN is like a virtual switch. You can take more ports. You can increase this VLAN, take more ports and have less VLAN on the other, less ports to the other VLAN. So that's what really a VLAN is, a virtual switch. So you have a physical switch that you can make into multiple switches. So here on this switch, you can have three VLANs, VLAN 2, VLAN 3, and VLAN 4. VLAN 1 is always there for you with all the ports in it. And then you can take ports from VLAN 1, put it into VLAN 2, and so on. So you can have, like, instead of purchasing three switches, you can split the switch into three VLANs, 4 or 5, as many as you want. and then take ports from VLAN 1s where everybody resides, and you can increase and decrease the amount of ports in each virtual switch or virtual LAN. Okay? So write this down. VLANs provide a way to group devices within a local area networks. It also allows you to do segmentations. So write all these bullet points. Those are the advantages of creating VLANs. The spanning tree protocol is really designed to make sure that you can have redundant links between switches so that when a link breaks, you will have a system fault tolerance. The other link will pick up immediately. But STP has to be running, because if you just run two links together, you are going to have, because of the broadcasting that the switches do, looping. Frames will loop around and nobody will be able to communicate. So STP will to make sure that the data does not loop. When you have multiple links, more than one link attached between switches. Okay? So what do you need to, oops, sorry about that. So let me just go back a little bit. I need you to write. Take the first 1, 2, 3. In fact, take all the bullet points for STP, because that's the only slide that's going to be discussing it. So if you have any questions about STP, I know we covered it in our CCNA course in details, please ask, okay? Because hackers, we're going to be protecting some of the ports, like to use STP to make themselves as the root bridges. I don't want to get into details about that, but if you don't know what a root bridge is and how STP operates, to make sure that you have a loop 3 path so you can have multiple links connected between switches, please ask. Anyway, so write this down. Multi-layer switches, or in other words, for layer 3 switches. So what's the difference between a router, a layer 2 switch, and a layer 3 switch, or sometimes we call it a multi-layer switch? So a switch is a layer 2 because it only operates at the frame. It reads the frames, read the labels that are stamped on the frame. A router is a layer 3 switch because it goes inside the frame and pulls the packet out. The packet is a layer 3 and reads the labels on it. So what is a layer 3 or multi-layer switches? Well, routers operate, they also not only be able to have access to the router, the packet that's inside the frame, but they can do routing. They run OSPF. They can connect to the outside world, do serial ports. They can do many, many things. But if you want to connect LANs or VLANs together inside your enterprise network, inside your campus, and you're not designed to go outside, you don't want to run OSPF or anything like that, purchasing a router to do that may be a little bit of overkill. So what they did is they took a layer 2 switch, gave it the software, the intelligence to enable it to go inside the frame, pull the packet out, look at the destination IP address, and send it to another VLAN. That's primarily what a multi-layer switch does. It doesn't run OSPF or anything heavy duty like that. So it's a low end of a router, but it's not really routing. It just connects LANs together. But it's a layer 3 because it has access to a layer 3 packet to decide. All right, so the layer 3 switches, or the multi-layer switching, please write this down. This supports the layer 3 interfaces. You can have the interface act like a routed port, which is similar to the physical interface on a router, like a default router, default gateway, or you could have it as an SVI, a virtual VLAN interface. In other words, are virtual routed interfaces. So write these 2 bullet points down. Okay, again, we discussed this in our CCNA, and we will have labs on even with the packet tracer to do some of these exercises. Okay, so here's a typical routed ports. So this could be the, the default gateway of VLAN 20. This could be the default gateway of VLAN 20. So that's what a routed port is. Hardly ever used that way. We use a router to do that. So a routed port is a physical port that acts similar to a router. So write this down. So also write the second bullet point. Unlike an access port, a routed port is not associated with a particular VLAN. It behaves like a regular router interface, just like the default gateway. A switch virtual interface is, the interface is for a VLAN. Remember when we thought interface VLAN 99 and we give it an IP address? That's what an SVI is. So write the first bullet point for the SVI. All right, so now let's take a look at the wireless communication devices. All right, again, it's always a good idea to watch these videos. These videos are very, very helpful. This is a 12-minute video, and I think it goes over all that you need to know about wireless in general. So that's a good review. All right, so wireless uses the RF signal to send the data. So your media is the radio frequency of 5 gigahertz with the 2.4 gigahertz that we're operating. So your wireless is operating under the 802.11. So the IEEE 802.11 is for wireless. The 802.3 is for Ethernet. All the LAN protocols and WAN protocols are housed, the standards are housed in the Institute of Electrical and Electronics Engineers. So everything is in there. So if you need to know anything about Ethernet, you go and read up on 802.3 and all the different variations, the 10 gigabits, the 100 megabits, and so on. If you want to learn about token ring networks, 802.4. If you want to learn about FDDI, the Fiber Distributed Data Interface, that's 802.8. And wireless, 802.11. WiMAX is 802.16. Bluetooth is 802.15. So they're all housed in there. Okay? I think you know about how wireless LANs are different than LAN. So with wireless, the 802.11 is primarily, although you can have two 802.11 devices talk to each other directly, but it's mainly designed to allow wireless devices to connect to a wired network. Okay, so you'll have an access point, like your wireless router, that's connected wired. It's wired to a switch. So everybody who has wireless, they has to connect to the access point, and then the access point will send the data to the wired. So if you have a wireless laptop, you're sending an 802.11 frame to the access point. The access point will remove the packet, puts it into an 802.3, an Ethernet frame, and puts it on the wire and sends it through the switch to its destination. So its primary job, the access point, is to connect wireless devices to a wired network. Okay? Anyway, so add all of these, write all of these bullet points so you'll know the difference between the wireless LAN and the wired LAN. Okay? And I think a lot of this is self-explanatory, if I'm not mistaken. Take a picture of this. This will give you differentiate between the quick summary, to differentiate between the 802.11 and the 802.3 Ethernet LAN. So the physical layer, the media, the radio frequency, 5 gigahertz or 2.4 gigahertz. Here you got cables in the 802.3. It either could be fiber, copper, or even sometimes coax in the old days. This is collision avoidance. The way you access the media to make sure you want to avoid. So in other words, you will send a signal to the access point. You tell them, I'm ready to transmit. Let me know when you are free. And then the access point will give him a signal, tell him, okay, now you're okay. This is like in the airport when the tower tells the airplane you're ready to fly. Collision detection is there's nobody telling you anything. You jump in and you try to detect if you hit somebody or not. And then you can go over the rest, okay? Okay, the frame of the 802.11 is a little bit longer, so there's a lot of addresses. You got the this is the MAC address of the receiving wireless device. This is the access point address. This is the MAC address, the source MAC address, and address 3 is the MAC address of the destination, right? Usually we don't use address 4. This is for ad hoc if you're directly connected. Then you got the sequence control number, the payload. The FCS is just to make sure that the frame is not corrupted when it's received, right? The frame check sequence. Okay, these are good to know. I'm not going to have you write them down, but it's okay. But CSMA/CA, this is a good review on how it operates, how wireless devices connect to the access point. They are always half duplex, means when you send data, you cannot be receiving. So either you send it or receive at the same time. You cannot do that. Okay. You have to just think of the CSMA/ carrier sense multiple access with collision avoidance. Think of when you go to the airport and you're on a plane and the captain on the plane communicates with the tower, telling him, I'm ready to go. Just let me know when the air is free, when the space free, so there is no collision. So we're trying to avoid collision. And then the access point, which is the tower, is the guy that tells the airplane, okay, you can go right ahead. This is like telling the access point, telling the PC you can transmit data. You can start transmitting. So write these down. Okay, so write these down as well. So this is what a wireless client communicates back and forth. Okay, so by default, the 3 steps that you do to connect to an access point is you are going to discover the wireless. You're going to authenticate, sending your username and password. And then the access point will authenticate you, validate, and then he will associate you, connects you to the network. So those are the 3 steps to complete the process. Okay. Routers, you must have an SSID number. I'm not going to go to subscriber set. The SSID is the name of the network that is available. So when you're looking for networks, what's being displayed, the name of the network that you can connect to, that's called the SSID. You need to have a password to type it in so that your device can send it to the access point, and the access point will configure it, will authenticate you. Now, your device, you can be running on the mode. You can be on either A, B, G, N, A, C, A, D, or even AX, the new one that is available. So some of these are backward compatible, others are not. Security mode is when after you are being authenticated, how is your data that you're being transmitted between you and the access point? How secure is it? The most widely used is WPA3, which is the newest one. Okay, so this is definitely, you want to be able to set that setting on the router. And you write in your network, and once you're connected, you'll use These will create random keys to encapsulate your data, randomly picked up. So if you close your session, those keys are gone. So that's why they are very, very strong, WPA and WPA2. WEP is the least secure because they use the same key to authenticate and encrypt your data. WPA and WPA2 doesn't do that. They'll use the same key to authenticate, maybe 3 or 4 different keys, but once you authenticate, then the data, your data, when you're communicating, they use random keys. So it makes it much, much more difficult to crack. And WPA3 is even stronger. The channel settings is how wide the frequency you're going to use. The channel is the frequency bands that are used to transmit the data. Please write these bullet points down so you'll understand what these mean. The wider the channel, the more data that you can send to the to the access point. Your access point always beacons. Beacons means you're sending out your SSID, supported standard, your 802.11 or whatever, and security, saying I'm WPA2. That's what you're beaconing. Okay? Being passive, you're just sitting around and probing the network. So you probe for the SSID, and this guy may respond back to you. Okay, that's what the access. Here's a typical router, right? This connection right here is your internet, if I'm not mistaken. That goes to your switch or your cable modem, right? And these are just 4 switch ports wired. And this is MIMO, MI, right? Multi-in, multi-outputs allow you to have higher performance, right? Okay, and okay. I have to get into everything else. That's a typical router. Okay, so if you have an enterprise network and you have a lot of big, let's say, building and you want to connect them wirelessly, you may want to use a wireless LAN controller. So the wireless LAN controller connects a lot of light wireless APs. They connect to the wireless controller. So a lot of APs connect to this wireless controller. The wireless LAN controller, you configure that, and that device configures all the other LWAPs all over the building. So so you can have a whole building connected into a network, but all you have to do, they all have to be physically, all the LWAPs connect to the wireless controller, right? So write the first 3 bullet points, all the bullet points. I don't know why I keep saying the first 3. So this is important so you can say, if you have one AP, that's fine. But if you have multiple APs, it's probably best to have a wireless LAN controller and have all of these devices connect to it. And it's much easier to configure this is like the central port that controls all of the wireless access points all over the building. All right, and that ends the chapter. So please take all the notes that I asked you to and submit them for proof, and I will see you on the next module.